Hello everyone, it's my pleasure to participate in the EAR ChinaCon conference. I'm Yuchen Shan, and my institution is Zhejiang Normal University of China. The title of my paper is Fog-based data offloading in urban violence sensor networks with discounted rewards, a contextual bandit. There are 5 main parts to my presentation today. Part 1, Introduction. Our lives are increasingly dependent on smart devices that collect data from the environment and operate in the physical world. Many IoT devices are deployed in cities as well as in metropolitan areas for security, surveillance, traffic and pollution monitoring, enforcement, and energy management. The proliferation of urban IoT applications has created an unprecedented amount of data. Due to the resource constraints and battery power, IoT devices are generally unable to process this data locally and usually rely on the cloud for data analysis and long-term storage. The traditional centralized-based cloud computing architecture generates larger lanterns due to the distance between terminal devices and cloud servers, which has made it difficult to meet the lantern's servers' requirements of hard real-time applications. The centralized-based management architecture is also difficult to support the access of a larger number of heterogeneous devices. To overcome these limitations, the concept of fog computing was proposed and applied to urban scenarios. Fog computing is a decentralized computing infrastructure that is located between the end devices and the cloud. The Figure 1 illustrates the 3-tier architecture of fog computing, adding a fog layer to the traditional cloud and end devices layers. Fog computing is an extension of the concept of cloud computing, which uses many devices in edge networks with extremely low latency data delivery. There are many application scenarios for fog computing, as shown in Figure 2, such as healthcare, smart cities, and so on. Sensor nodes can only effectively support urban applications if they foster successfully transmit data to the fog nodes. This mission is known as data offloading. Nevertheless, the limited storage resource of this sensor prevents them from keeping the data they generate indefinitely. It is therefore vital that data is transferred to resource-rich nodes before storage space is exhausted. We refer to this problem as the data loss problem. Given the dynamics of the urban environment, the data offloading problem can be constructed as a non-stationary CB problem. The kernel UCB algorithm is a nonlinear algorithm based on the MAB model. The algorithm assumes a nonlinear relationship between reward and contextual information. The nonlinear contextual bandit robust for data offloading algorithm based on the kernel UCB algorithm is proposed. The algorithm assumes a nonlinear relationship between the reward obtained from offloading data and the dynamic heterogeneity of the hypernodes in the fog node network. In addition to this, a discount factor for historical rewards is introduced to improve the kernel UCB algorithm, taking into account sudden changes in the urban environment. Part 2. System model and problem formulation. The nodes that need to perform data offloading are called task nodes, and the nodes that receive the offloading data are called helper nodes. In each period T, the process is as follows. Number 1, the heterogeneous information xtn is feedback to the task node as a vector. xtn is the context information of helper node n at time slot t. Number 2, selection of helper nodes. The task node observes heterogeneity information and selects high-quality helper nodes based on the rewards observed in historical trials. Number 3, rewards feedback. The foregoing nodes feed back to the reward to the task nodes. Objective function. Without loss of generality, we normalize RTNT belongs to 0 to 1. Our goal is to achieve a high level of upload success rate with the reward equal to 1 when the selected helper node completes the data offloaded and 0 otherwise. The aim is to maximize the above expected total reward. The mean value of the reward distribution on the optimal helper node in each round is VTOPT. In the MAB framework, the regret value is used to measure the performance of a bandit algorithm. The regret value is described as the difference between the total system gain obtained with the best string in the ideal case and the total gain obtained with that string. In the time-varying case, the mathematical expression for the regret value of a non-stationary bandit after t time slot can be expressed as follows. Equation 1. Part 3. NCB-RDO algorithm design. Kernel method provided a way to extract from observations possibly nonlinear relationships between the context and the rewards, while only using similarity information between contexts. For the nonlinear CB model, we assume that they are exerting a mapping function phi, mapping data to the Hilbert space, for which phi their existence theta belongs to H. Therefore, for expected reward is linearly related to the heterogeneous information of the helper nodes as follows. Equation 2. According to the mapping function 5, the kernel function is defined as this equation, and the kernel metric of date is denoted as this equation. First, the estimated value of reward, this equation, needs to be predicted, where theta t is the minimum value of the regularized least square function, equation 3. This is used to denote this function. Let L theta be equal to 0, and the following equation 4 can be obtained by taking the partial derivative of theta. Equation 4. Equation 4 is rearranged to get this equation. The kernel metric is used to express this equation. So the equation 5 is obtained as this. Next, the width of the confidence interval for the predictive value of the rewards needs to be calculated. For linear bandits, the appropriate bandwidth is constructed based on the Mahalanobis distance of phi from the metric phi, equation 6. After equations transformation, we can express this as the following equation. The above equation is rearranged to give the expression for the weights of the confidence interval as equation 8. This equation deals only with the inner product between elements. At each time slot t, the algorithm selects the haploid satisfying equation 9. And we focus on a discounted MAB formulation that allows for a wide range of temporal uncertainty rewards due to the different demands of the dynamic urban environment. To estimate the instantaneous expected reward, this scheme averages past rewards with a discount factor that gives more weight to the most recent observations. Adaptability to changes in parameters does mean reducing the influence of observation made long in the past, which means using weights that increase with time. At each time slot t, when a haploid is selected, the average value of discounted rewards and the number of discounts are given by equation 10 and equation 11. Part 4. Simulation experiments. The efficiency and the performance of the offload scheme are verified by the following performance metrics. Number 1, average reward is defined as the mean of the reward feedback after data offloading to the fork node. The selection count is defined as the number of corresponding haploids selected based on the CB model. It's used to test the robustness of the algorithm when the contextual information of the haploids changes abruptly. And number 3, success offloading rate is defined as the rate of success offloading counts compared to overall runs. The NCB RDO comes with 2 hyperparameters, including gamma and eta. To optimize these hyperparameters, we propose to perform a grid search as in Figure 2, where the value of gamma will be between 0 and 3, excluding 0, and the value of eta will be between 0 and 1. The results will be displayed on the grid with color bars. The experimental results show that the mean reward reaches a maximum of 0.70 and 7 when gamma takes the value of 0.5 and eta takes the value of 0.3. Figure 3 illustrates the change in the success rate of data offloading as the number of trials runs increases for the 4 considered offloading schemes. The NCB RDO algorithm could achieve an offloading success rate of 80.20 and 8%. The lean UCB algorithm could achieve an offloading success rate of 70 and 4.167%. Compared to the first 2 contextual bandit algorithms, the UCB algorithm and the epsilon gradient algorithm have a low offloading success rate of 16 and 5.6 15.83% and 56.6% respectively. Figure 4 illustrates the change in the average reward for the 4 data offloading scenarios as the number of experimental rounds increases. High-level success of loading rate is linked with the contextual bandit rewards. To obtain a higher reward, the gamma in the NCB-RDU algorithm was set to 0.5 and the eta was set to 0.3. The average reward of NCB-RDO is higher when compared to the other 3 schemes. And the robustness of the LinUCB algorithm and the NCB-RDO algorithm was tested in a highly dynamic environment. The state information for node 2 is assumed to be initially good, larger memory margin, faster transmission speed, and so on, while the state information for node 5 is initially poor. Figure 5 shows that the number of selections and the node state informations are positively correlated. 1T means 700 help node 2 and 5 suffer an abrupt change. The state information of node 2 is poor, while that of node 5 is good. As shown in Figure 5, the NCB-RDO algorithm is more sensitive to changes in contextual information compared to the LinUCB algorithm. Part 5 Summary. The multi-source data offloading problem is not a simple overlay of the single-source data offloading problem. Therefore, our next work will consider a coordinated multi-source data offloading scheme based on a contextual bandit model. Thank you for watching. My presentation is over.